Okay. Hope everybody enjoyed their snack break. I'd like to welcome for part 2 of her Meteorite presentation, Sandra Macika from the Ford Amateur Astronomy Club. And if you weren't here at the last meeting, some of her biographical information. She's a lifetime member of the San Jose Astronomy Association. She's a current member of the Ford Club, like I said. She's still the owner of a 14.5-inch Starmaster telescope. She got that in 1999. She worked at Lick Observatory in public outreach for 10 years. She worked at NASA, the Meteor Shower Studies, for 7 years. Starry Night Supervisor at the Wayne Oakland Science Olympiad since 2014. She has a Meteorite Tektite collection of over 100 pieces. And she does public outreach with a collection of schools, scouts, and astronomy at the beach, astronomy clubs, and other public venues. This is part 2 of her Meteorite presentation. This is on chondrites, and she will talk about the composition, formations, and she might be answering some questions from the previous presentation that you did, I think you were saying, right? No?
No, that was during the break. You got to read the screen. And
okay, so that was all taken care of. All right. Anyway, Sandra Macika, doing part 2.
Hi. Thanks for having me. So I'm going to start with a little bit of astronomy meteor humor here. So I'll just start this up. And it's kind of quiet, so if you could be quiet to hear it, I'd appreciate that.
Yes. When you go to the bathroom on Earth, you're relying on gravity pretty heavily. Imagine if you were halfway done and somebody shut off gravity, it'd be a mess. And you'd float off the toilet. So when we designed our space toilet, first it has to have a seat belt on it to hold you down. And then we decided to separate solids and liquids because they're easier to store that way. So we just have a tube that you pee into, and it has air pulled into the tube, so it's not a big deal. For the women, there's a cup fits up against them. For the guys, it's just like a little funnel. You just pee into this tube, and it goes into a sewage tank. But the solids that come out of your body, that's a harder problem to solve, and it's an important medical one, because on Earth, everything falls on the floor. But in space, it's going to float around. So it'll really make you sick. If you re-ingest something that came out of your body, it will really make you sick. And we can't afford to get that sick. So we designed a toilet that instead of gravity pulling everything into the toilet, it has air flow. There's air pulled down into the toilet. Sort of windy when you're sitting there, but it pulls everything out of your body. Everything that comes out of your body gets pulled out into the toilet by the air. And then in the storage tank, we just expose that to the vacuum of space, so it basically just freeze dries everything, so it kills all the bacteria, so that there's no smell, and then we just store it. And then when you have a whole bunch of it stored, we put it in a little unmanned supply ship, and we undock it, and it burns up in the atmosphere. So the next time you see a beautiful shooting star going across the sky, that's what it might be.
Colonel Chris Hatfield.
That's great.
So now this is so far away from that. If I want to change the picture, then I have to keep running back over here.
Oh,
I guess that's
I
what
can
I'll
run
do.
the.
Thank you. Okay, this is actually an old picture of my collection, and I think these numbers are old too. I guess I didn't update that one. I've got, I think, about 70 pieces of meteorites and I think 33 tektites, maybe 75 meteorites. So it's just over, I think it's about 105 total pieces I have. And that's an old picture too, but that's most of the meteorites and that I have. Thank you. So I'm not going to go through the whole introduction that I went last time, but I just want to remind the difference between a differentiated and undifferentiated, which is today we're going to talk about undifferentiated meteorites, meteorites that come from an undifferentiated parent body. Last time we talked about differentiated, which I'll just remind us that's a differentiation is when a planet is large enough and therefore hot enough so the things with the lower melting temperature will melt, and then the gravity will bring the heavier items to the center, so the nickel iron will come to the center, which is the core. And then the next layer will be the mantle, which is mostly olivine, and then the very thin crust. So that's when you have a larger parent body, it will be differentiated like our planet Earth. And meteorites like this, or a body like this, has gone through many changes from when it first started and then got big enough and then got hot enough, and all this melting and changing is very different than how it started out. So if we could go to the next slide, please. Today we're going to talk about undifferentiated or chondrites, which are very interesting to scientists and astronomers because they haven't gone through these changes that the differentiated ones have gone through. And so we can see what we can look at what planet formation is like. We can see what the planets were like when they first started to form. So undifferentiated, it has gone through some changes. There's some heating involved, and the nickel iron will tend to beat up. And some of these meteorites, when you look at them and you look in the light, you'll see the little shiny specks everywhere, and that's the little bits of nickel iron in them. Good, thank you. And so let me just back up for a moment and make sure we all know what a meteorite is. The difference between a meteor and a meteorite, we're kind of talking about that up here before. So most of us, I think, here probably know the meteor. A meteor or a shooting star is not a star at all. It's something like a little rock or a piece of metal from the core of a planet, or it can be something even small like a grain of sand. And what happens, it starts out in space, it's called a meteoroid, and then when it comes to the Earth's atmosphere, the friction actually causes the air around the item to burn. Not actually burn, more ionize. It's kind of like it's burning, but it's actually ionizing the air. So when you see, it's not the actual piece of rock. Obviously, a piece of rock doesn't burn. It's the air around it that's ionizing. And that's what a shooting star or a meteor is. And then if it lands on Earth, what I have here today are meteorites. And now this explains the difference between the names of what we call from undifferentiated and differentiated. It starts out in the planet formation as a planetesimal. I used to use these words like interchangeably. I thought they all meant the same thing, but I actually looked them up and found out planetesimal is the undifferentiated, or the bodies that a chondrite would come from, the smaller bodies. And as they get larger and become differentiated, that's when they're called a protoplanet. And then a planetoid is something completely different. Just so we know the terms here, that's what we call a dwarf planet. Like the Haumea that we saw, I was really surprised to see that that has a ring around it. That was really interesting. Next one. This, I know you can't read all the details in it, but this we're going to zoom in on certain areas. But this shows the whole breakdown between the undifferentiated and all the different, oh, sorry, go back.
Oh, this is a zoom in.
We're not zooming yet.
Okay.
So this shows the chondrites here, and we will zoom in. And then this shows the differentiated ones that we talked about last time, and the different groups here. So we'll go ahead and zoom in now to the chondrites. And basically they come in, the first group is the ones that are close, this would be the one that's the very top, is the closest example of what the planet looked like when it first started, the planetesimal looked like when it first started to form. And these would have the most oxidized iron, where these have less oxidation. And these will have more iron, and this will be less iron. And this is the least melting temperature, and this is still low melting temperature. I think is this all showing on the screen?
No, it's only, well, it's only
It's cutting off the bottom there, isn't it?
You got it.
Yeah.
So-
I have to scroll around.
Why doesn't it all show on the screen at once?
Because we're zoomed in.
No, I didn't want to zoom in, I just want to see that one picture, the
Oh.
whole picture, like, I'm sorry, go to the next page, please.
Okay.
There, this shows,
Aha.
this is my zoom in.
Okay.
I zoomed in by going to the next page here. So then this goes to the last group here where we have the least melting temperature. And this would actually be the least oxidized down here. So we're going to start up with this group right here. And there's a few of them here, this example right here, the primitive. And the primitive is kind of a strange term because many people call all of these primitive. And in a way that makes sense because these are the ones that are like the very first, as I explained before, when the planets were first starting to form. So that's like primitive, right? But there's a specific scientific name like the books all use to explain that these are referred to as primitive. And if we could go back just go back, the differentiated has a few groups of primitive too, which to me that name doesn't even make sense why they would call those primitive, but that's what they call them. So that's going to be another topic, and I'll talk about primitives separately in part 3. So today we're not going to talk about the primitives. If we could go again to this page, and now we're ready to go one more page. So chondrites, what's interesting about these, and actually all meteorites, but these are even older than the differentiated ones because they haven't gone through those changes. But this is like the oldest thing you'll ever touch. Everything on Earth, although the Earth they estimate to be 5 billion years old, so everything is, it started 5 billion years, but everything has changed. Nothing is like it was, even 4 billion years ago, because plate tectonics and everything that goes on in planet formation and just even wind erosion and rain erosion and volcanism, everything is constantly being changed. But these are the same as they were like 4.5 billion years ago. So this is really the oldest thing that's still in that same original state as it was 4.5 billion years ago. And the chondrites all have these little droplets in them, which they call chondrules. It comes from a Greek word called chondroin, which means like a little granule or a seed or grain, and that's why they call them chondrites. Chondrules are the things in them, and then the meteorites themselves are called chondrites. So go next, thank you. And this shows what I was telling about, that the meteorite is very much like when we look at what the sun is made of. The sun is made of the material pretty much the solar, when we have planet formation, we look at the whole formation of the solar system. There was like a cloud, a nebulous cloud, and the sun formed, and then this cloud was very much like the sun was at that time. And then the first planetesimals that started to form were also very much like the sun. And then as they changed, we'll see that, and this shows how when you compare, this is an example of one of the Carbonate Chondrites, one of the ones at the very top of the list that I showed you were the closest to what the sun was like, or what the planets were like when they first started to form. And this is each chemical, how much it had, the sun has now. So just take an example like potassium, that's how much in this millions or whatever of how much the sun has. And this is how much the Carbonate Chondrite has. Everything almost exactly the same, except of course the gases that the sun has, then these don't have those gases at all. Excuse me.
And it's just the rare gases? Argon, neon, and helium?
Those are, well, there's no gases in there's very little gas in a chondrite. And the sun obviously has a lot of gas in them. So these are all zero for the chondrite, although there's like a lot of helium in the sun, for example.
And the oxygen and hydrogen up there are just combined with other materials.
Right.
Yeah, to be oxidized.
Right, so
You can find little bits of gases, and that's how, for example, that they know the meteorites that I talked about last month, that come from Mars, where they can analyze little bits of gas that is left over in the meteorite. So there are little bits of gas, and then they compare that to what they saw in the what they can see in the atmosphere of Mars by using a spectrometer, and then they can see that that gas is the same. That's how they know that those meteorites came from Mars, because there is just little traces of gas. So if we look at another example of a meteorite that that's not a chondrite, we can see that it's all over the place, that it's not like the sun at all. Where, where this one has this particular element, there's a lot of it relatively in this meteorite and very little in the sun. Nickel, everything is completely different. So we can see that the chondrites, especially the very early ones, are very close to what the solar system, the sun and the solar nebula was like in the beginning. And this is a picture magnified of a chondrule. And we'll be able to see, when I pass around these meteorites, you'll be able to see the chondrules in them. Next, please. And this also shows the chondrules. The colorful bits are the olivine crystals. And this is when, unfortunately, we won't be able to do this experiment because there was a misunderstanding about what I need for a polarized filter. If you have a thin slice of a chondrite, like for example, I have a couple of these real thin slice ones here. I'll pass this around so you can see it. Then you put a polarizing filter on top and below and the sample in between. And then you shine a light from below, and then you look down on it with a magnifying glass, and you can see the colors of the olivine crystals are very beautiful like this. The ones I have only have a few spots of these colorful crystals. These ones that are very colorful like this are very expensive. So if you could go to the next, please. So now we're going to start looking at this group of the Carbonate Chondrites, which have more carbon than the other types. And this shows pretty much the same thing that the last one shows about the iron and the oxidation. These colors match the previous slide where each type, it shows how much oxidized iron. So these purple ones and the blue ones have a lot of oxidized iron where the yellow ones don't. If you could go back previously. So, no, not this one. Yeah, this one. So these yellow ones, for example, are the least oxidized, and these are more oxidized. And go forward, please. And this shows you basically just the same thing there. So the Carbonate Chondrites, or the C chondrites, this is what I was telling about, the most primitive. Okay, let's go ahead one more. So now we're going to go ahead and start looking at the types I have. I'll describe the first bunch, and then I'll pass that bunch around. And the first bunch is the Carbonate type. And I don't have any of the first two groups, I believe. If we could go back to that one, please. The first one is CI and then CM. I have CM, but this one is very expensive. I haven't even found one of these for sale. But I have some of these here. I have all of these groups here. So go ahead to where we look at my first sample. Thank you. And this is the CM type. And this just tells you a breakdown of a lot of the things. And you can see this is a small piece. This is a cubic centimeter here. And what I look for when I buy one, I look for ones that I like to try to get one in each of the different groups. So I'm still looking for that CI type. And I think there's a few others, the CH I don't have as well. But I also look for ones that have a fusion crust on them, and not all of mine do, but most of them do. And I also look for the most interesting chondrules that have different colors and different shapes and different sizes. So that's one of the reasons I picked this particular piece, because that interesting inclusion of in there. And I have all the facts here of last time we talked about the difference between a fall and a find, and I'll try to highlight the ones that actually are finds because they're more the ones that are falls, which are more interesting. A find is if you just found it. If it's called a fall here, that means that somebody actually saw it and then recovered it. So those are just kind of fun that way. And when you look at the total known weight, if it's just in a matter of grams, that means it was a smaller one. And some of them I have where the total known weight is, less than 100 grams, and that means they're more rare because that particular type there wasn't a lot obviously to be available. And if they're in kilograms, that means there was more available obviously, and so they're more common and you can find them more easily. And then the physical characteristics will just describe what you see here. And I've had people talk about like buying meteorites on eBay, like how do you know if it's really going to be a meteorite or not? And if you look at the meteorological bulletin, that every meteorite has a bulletin on and will describe the characteristics. When I have this physical characteristics here, these come from the bulletin. And the bulletin will also have pictures. And you can look and see, does this look like with the pictures on the bulletin? And they match up like, one type of meteorite only looks one way. So when you look at a picture of one that's being sold on eBay and compare it to what the bulletin shows you the picture, then it should look like that. And so whenever I buy one from eBay, I usually do that kind of comparison.
Could you use a laser pointer?
No.
Oh, you got one? I'm sorry.
Okay. And I also just show you for reference, you can kind of see that this is a very small sample and the price. When you sell one on eBay, they often go for bids, and so the bid, the price can be anything that anybody is willing to pay for it. And they usually start very, very low, but then they go up. They never sell for what the person starts them, they might be only start at like $1 or something, but they never sell for $1 or whatever. But when you look for meteoritesforsale.com, which I buy a lot from too, when they have a certain type of meteorite, like this NWA, this particular number, that's a specific meteorite. This is the type that it is, but that's a specific type. And when they have one type of meteorite, they'll have several samples, and it's the same price per gram. So it just basically gives you an idea of the value of that meteorite.
What is the severe thing?
Oh, some of them, they don't all have it, but there's S and W, which is the shock and the weathering. And so this has severe weathering on it. All the meteorites of this type, not this particular piece, but this meteorite in general has severe weathering. And this is one, for example, that if we could have done that experiment if I actually had the polarized filter, but we can see here the little specks of the pretty colors that you would see with the polarized filter. Excuse me. And this is the CO type. Okay, next please. And here's two more of the CO type. And a lot of them, you'll see the NWA, which is Northwest Africa, and they have a lot that they find in Northwest Africa because it's like a big sandy, it's not like a sand desert like the Sahara Desert, but it's big open fields of just dirt, basically. So when you see some rock of a dark color or whatever, you can run right over there really quick and probably it's going to be a meteorite. And so they find a lot of them there, as opposed to, obviously if it lands in the ocean, you're not going to find it at all. Or if it lands in the forest, it's going to be very difficult to find. Most of the ones that they find, if it wasn't from a fall, which are a very small percentage, the ones that you see, but the ones that they find through farming. So if you want to find meteorites, that's the best way is to be a farmer, statistically. Okay, next please. And this is just another group of the CVs. And the letter that they have is the group, that particular type, based on how much oxidization it has, how much iron, how much carbon in it. That's how they're grouped into different groups like that. but the name they get, the letter, is usually from like the first find or maybe a big find. Each meteorite tends to be named, if it doesn't have a number like this, they're named after the city where it was found in or near. And this is the city in Italy where that was found, and this was a very early one, and that was one where they saw it fall in 1910. And that's what the CV group is named for. That's why it's V, is this V of that. And then we get in the CK group, and just some more examples, but I think that's the last one in this group. So I'll go ahead and pass this around now. This is the group of these, and these are the lowest, have the lowest metal. And last time I passed around the magnet, and when we looked at the ones from the differentiated, like the ones from the iron core, boom, they stuck in. It was like hard to get them off. And this has the lowest metal, so they will stick to this magnet, but it's not allowed to pull it off. And the ones with the most iron and the most nickel iron, which is this group here, they stick obviously more than that group, but nothing like the nickel iron ones that I passed around last time. Like my ring here, for example, where this is from the core of a planet that I showed last time, and that really sticks. Is kind of difficult to pull apart. So I'm going to pass around the loop with that, and to show you how this, you can turn the light on with this little switch right here close to the hinge. And then there's more than one way to do that, but the way I do it is put my eye, like this is touching my cheek, I rest it on my cheek, touching my eyelashes, it's that close. And then you just pull this very close to the distance where it's in focus, and that's how I look at it. And this one's really neat because it's got chondrules inside the chondrules. Let's go back and look at this one. Can you go back until I find this one, right? Go back. That, no. There. This one, and I can't see it on here. I'm looking at the other side of it. And I don't see them on that side, but when you look on the opposite side that's not showing in the picture there, you can see little light browns inside the black chondrules, and they can form like that. So I'll pass this group around now. This is the carbonate group.
Is it okay to just leave the loop on?
Well, no,
Okay.
because it might burn out.
Okay.
So the ones, I don't know if those are all, if I have the lid open, that means you can look at it, touch it. I encourage you to touch it, pick it up, look at it, look at the fusion crust. If the lid is closed, please don't open that, because it's probably one that's really super fragile or super expensive, or maybe it's already broken or whatever. So the ones, most of them are open, and I encourage you to go ahead and actually physically touch them.
Oh, sorry. Yeah.
Okay, so that was the group of the carbonate type. And now we're going to go to this next group, and I'm going to start with these L's, which are low iron. And these are the lowest iron, but these, in the next group, these are lower than these, the L's. So when you look at the name, which is on the side of the box, if it has, you can see the L's, and the L's are like numbered from the LL is the lowest, and then a single L is still low, but this is lower than the L. And then they have a number, like L5, L7 would be the highest amount of iron in that group, where LL3 would be like the lowest amount of iron in this particular group.
I got a question about the iron containing meteorites that have been significantly oxidized. Is that mostly from weathering?
No, this is how they were formed. This doesn't come from weathering from the planet. These are like the way the meteorites are.
So the oxygen was not there.
And the formation of the planetesimal.
Okay. And would that be the same for the sulfide?
I'm not sure about basically weathering has very little, you know, the weathering, for example, like the one that I showed last month that we were asking about that has the, actually it's not that one, there's another one that has holes in it that we're gonna look at, this one actually, when we get to this group, where it has very severe weathering. This is, we've been on Earth for a long time, and the iron is almost all gone from it because of weathering. But in most cases, when you look at the content of it, the weathering doesn't have a lot of effect on like how much percentage of what different chemicals or what different elements are inside that meteorite.
So if it's got oxygen, it's probably because it came down with it.
Right, exactly.
And you can tell, like, from the shape and how it's pitted or whatever, whether or not it's been weathered, you know, for how long it's been sitting there and getting weathered.
Right, and that's going to be more, like, these get cut up after that. So you'll only see that pretty much on the surface before they're cut up, the weathering effects. Unless it's really severe like that one example. So let's go back to that other picture.
Whoops.
Yeah, this one. So this just, now we're getting into the group of the ones, the LL3s. And this is the shock has less and this has more weathering. Some of them they actually have a number where the lowest means number W0 would be the least weathering, and W3 is the highest I've seen. I've also seen it called weathering severe, and I'm not sure what the highest number is, but the 3 is the highest that I have. So these are just some more examples from Northwest Africa. This one has a really nice inclusion. I like this little guy in the very center. And this, again, I chose this because this big black inclusion here and the large different color chondrules and the whole, you can see that this has very little matrix and mostly a lot of chondrules. And they don't really know how these chondrules were formed. They know that it was a high heating, something with a high heat that happened very quickly formed. And there's several different theories. And the one that looked like it made the most sense to me of the theories that I read were where they talked about how a star, where they see stars that have new formation, where they have these big jets of like heat coming off of both sides of it. And they think that the sun, when it was forming and it had these jets, like the material got in there and got heated and got thrown then into the area in the asteroid belt where these come from. And they don't know, but that's one example of how they might have, these chondrules might have formed.
Question? So the chondrules have been heated, but not the material that it's in?
Well, the whole material. These are like lava bits. So it's what the material is made of that cause, you know, the heating. Something with a lower heating temperature would form the chondrules, and other elements that didn't have as low a heating, a low of a melting temperature would not turn into those little lava bits like the chondrules do. And here's an example of another thin slice where it only has like a couple of those bright colors. And these are expensive. This is with this thin slice. They don't even say how many grams it is, but it's very little amount of grams that you're getting at this thin slice. But I really like the colors, so I went ahead and got that. This one's a nice example because when I pass these around, this has a big surface and it's got this square box like you can see there, so you'll know this is the one. And so it's got a lot of the fusion crust area on it. So I encourage you to, you know, go ahead and look at that. That's really interesting. And this one has these, you can't really see it so much on there. I think this is the one though, yeah. And the, somehow it's the other way. It's flipped. Okay, this side isn't showing it. When they described it, they call these angular clasts or rock fragments. And the other side, which is how I happen to have it in the box, you can see these are all angled. and they're long and an angle shape. For some reason it's not showing on that. I'm going to leave the angle shape up so you can see how that one has the angular class that are interesting. And there's a lot of diffusion crust area there too, which I like about that particular piece. That wasn't a very expensive one. It's small, it's only 2 grams, but it was very expensive. And this is L5, so we're getting into more metal content. And these are the ones, the next group, when we get into the H's, you'll see it even more. But when you look at these in the light, you can, if you get the light shining on it just right, you'll see all these bright specks, which are the nickel iron, and they're very beautiful. It has a lot of the fusion crust area on it too. I like that about it. And this one is the Chelyabinsk, which happened in Russia, 2013. It was a fall. It was a huge event. Probably a lot of people heard about this one, where there was camera footage, and we'll see a very short video about it. And it happened during the day, and it was brighter than the sun. People describe it as brighter than the sun. The trail it left stayed for hours, and I've got a lot of information on this one. I won't read everything here. It fell in fell into a lake that was covered with ice at the time, and it formed a 7-meter hole. And the largest sample was 654 kilograms. This question?
Oh, I was gonna, you said it would left a trail. What would the trail consist of, like dust or diminishing note?
That's just the ionized air that's left.
From it?
And when there's a lot of material, when a meteorite comes through, the meteorite itself doesn't burn, as I mentioned. It's the air that's ionizing, or it's like it's burning, that you're seeing in the glowing. But sometimes the meteorite can become hot enough where it'll start to melt the material, and the material will be left behind. And when you see a glow that stays for a long time, that can be the material that's left behind, still kind of hot and glowing because it was heated up and melted. And then, but the meteor itself, as it's heated up so hot and it's melting, but everything that gets hot and melts is immediately blown off because it's going so fast. And the wind is still going on the meteor, and it's just come from outer space, so it starts out really ice cold, like outer space, right? And so when they land ice cold. Every time they're cold. I've seen this in pictures like movies, maybe Superman or something like that, where there was a meteorite that landed and they came and it was like super hot, glowing red hot, which would never be the case, because anything that's heated goes off, and any other heat, as the friction, the air that causes heat, you know, the movement, the rubbing against the atmosphere of the air that causes friction causing heat, it's not enough to actually heat up the sample. And if it heats it up enough, or if it does start to heat, it's just the wind blows it and keeps it cool. So when it lands, it's going to be landing cold.
Thank you.
So this one is an example when you look on eBay to buy them, and you can see pictures of what this is like. Has this white part in it. A lot of them just look like little black rocks. Like without this white part, there's a lot of them for sale that are just black like that. A question?
If you go to YouTube, in Russia, most of the drivers have...
Yeah, we're going to see that in a minute.
Oh, yeah.
So,
Well,
so a lot of the ones for, I'm sorry.
This one exploded with the equivalent of a small nuke. It broke windows
Yeah, this talks about that here, how there was a few people who died and a lot of people who injured. I think like 1,000 people were injured from falling down walls and breaking windows and stuff like that, and a few people actually died. But this is an example when you want to buy one on eBay, there's a lot of these that are not open like that, and you just see the surface of that black. And there's a lot of them for sale like that look like just this black, like this part right here. And those are probably meteorites, the Chelyabinsk meteorites. But I don't know that for sure. I mean, they look like little black rocks, and they could be anything. And that's whenever I buy one from eBay or any source that I buy it from, and I compare it to the bulletin that, you know, I don't know for sure that they're meteorite, but if you can see, this looks exactly like the pictures from the bulletin. So then I know this is the meteorite. Next page, please. And this shows pictures of the trail. And I don't know if this will work or not. Let's try to click this. Oh, it's not working. It works on my screen somehow when you do this. So it's a no-go.
I think,
Jonathan is performing his magic.
let's see about that.
Well, anyway, if you go to Wikipedia and look up the Chelyabinsk meteorite, and you can go there.
Oh, it's not on the network is the problem.
Let's not do that right now, it's gonna take too long. If you look in Wikipedia, you can click there and see a little video of you can actually search and find lots of videos of this. That happens to be a nice little short one, but let's just not do that right now. So next, please. And this talks about because so many people witnessed this, and there were so many pictures from security cameras and police cars that had their, camera in the car and stuff, that they had all these sources to be able to determine the orbit of it. And they found out that it comes from this group of Apollo meteorites, which the asteroid, or the Apollo asteroids in the asteroid belt. And they know that almost all meteorites come from the asteroid belt. They've been able to determine from determining the orbits that they come from there. And also just by looking at the composition, they found a lot of them, like the ones we looked at last time, that they've determined specifically come from the Vesta asteroid. And this one comes from this group of Apollo asteroids in the asteroid belt. And this just happens to show a few of the other different groups of meteorites, which were probably, or groups of asteroids, which were probably originally one asteroid that broke up, and so all the bits are still in the same orbit with each other. And this shows specifically the orbit of the Chelyabinsk meteor.
I've got it here if you want me to plug it in.
What's that?
No, I think.
Oh, that video, it's just, you see the bright light, and you can find that easily enough in Wikipedia. And they have so much data, this just shows the strewn field. This is specifically what people saw, this yellow bit, and this red bit is where most of them fell here, and then each dot, the bigger the dot is, the more pieces they found in that particular spot, so less pieces here. And I don't remember which way this was going. I think I talked about last time, when you see a strewn field, it's in this oval bit like this. And the meteorites can go either way, either they fall in the beginning or the end. And I don't remember if this was going east to west or west to east.
On the left, is that the lake that they found the pool?
Yeah, that would be where they found that big spot.
So what kind of distance we're talking about here? I can't tell.
Let's see. The length of the trail, it was 246 kilometers.
Okay.
Entry velocity, 17.5 kilometers per second. Slope, 18 to 19 degrees.
Yeah, so 200.
And the altitude of the luminous trajectory, 90.
So it was well positioned to put on a good show for a while.
Pardon?
It was well positioned to put on a good show for a while.
Yes.
The angle and everything.
Okay, next please. If we can go back just a moment. This, this one. There's a lot of detailed information here, and this is on Wikipedia. When you look up that Chelyabinsk meteorite, you see that video, and you can also see this, and you can zoom in on these and read a lot of details about it. I just picked out a few of the most interesting ones.
So that, just for those not up on your kilometers, that's 153 miles.
Yeah,
Thank you.
You're the man.
This is an unusual one. It's just because the cut for one thing, but it also has a lot of, just because it's lighter colored, usually the matrix is a darker color, and really it has a large space, again, of the fusion crust area that's not where the cut is, and even in that area you can see the shining bits of nickel iron. We're still in the L group. This one was one of the very first meteorites I bought on eBay, and a lot of them have a centimeter cube next to it, so you know what you're buying, and I wasn't, you know, that savvy in looking at all the details, and I thought this one looked really interesting. And it was only $2.50, but then when I bought it, I found out it's a speck, and I wouldn't have, and it wasn't, you know, like a real huge waste of effort when you know, but I don't really want to buy specs, but I bought this, and so there it is. Next, please. And this is still the L group. This is these have the chondrules aren't well shaped into round circles on either one of these. They've got these. Some of them are, but they have these different colors that are really beautiful in both of those. And this is the H group. So now I'm going to pass through the. Have we finished passing through, looking at the first group yet? No, okay. So this one, the light doesn't work so well. It's a UV light, and so you can use this as a loop, but the light doesn't work very well. Where are we starting here?
Are those your fingers in the picture?
No, this is the when I bought it on eBay. That was the picture that came with it. So then this is the H group, which has more metal in them, and I don't have as many of these in the group. And again, I chose this one because of the beautiful colors and that particular inclusion. I like to pick ones with that have the pretty colors. No problem. And this is a larger piece, 5 grams, and a lot of nice colors in this. Finally, when there's some of these, the H, almost all of my, so that switch is a little flaky, sometimes you have to switch it back on and off, but it doesn't really light up very much anyway, that UV light. And these are the first ones. This is still from Northwest Africa. Almost all the L ones I have are from Northwest Africa. And this is also Africa. But here's one from Mali and Australia. So a few from different areas in this age group.
Are we about out of time?
Yeah.
We're getting there rapidly. We have 6 minutes.
Okay, I think I'm almost at the end of my presentation. Let's start this at the other end, at the very end of the group. Is the end here or the end there? You're going to go this way and come here, and let's start this one going in the opposite direction. And I have two from this Enstenite group. Which are the least common type of chondrites. And they have the highest metal content. And they think that this actually came from a different part of the solar system originally. It formed in a different part where it was close to the sun, like within the orbit of Venus, or maybe inside the orbit of Mercury. Or it may have come out further than because it's so different, they think it formed in a different area in the solar system. And this is the one that I talked about that's been on the Earth so long. The measured age is 23,000 years.
Oh, wow.
And this is the one that that has, where the metal was, it still has some metal, but a lot of the metal has completely disappeared from it, and it leaving little pockets inside of it.
The metal just rusts away? Is that-
Yeah.
Ready?
And it was a big one, 3 metric tons. I think this is just about the end of, there's my other end snake. And,
Does it do anything for you?
Next one is where I,
okay, so that's the end. Now we have time for questions.
Okay. Many decades ago, when I was young, there was a meteorite, or meteor, going through the atmosphere. It had a green cast. Would that mean it had a high copper content?
Probably not a high copper content, because copper isn't a high element in any of the meteorites, although some do have bits of copper. It's like the nickel iron ones, after nickel iron, which are like almost, they have very small, the next element is copper, but it's like less than 1%. So none of the meteorites really have a high copper content. They can have, I've seen different colors, and that can tell you something, but I'm not really sure about that.
Because of the recent confirmation of how some precious metals, the gold and platinum, were formed because of this collision of 2 neutron stars, have any meteorites been found with those rare elements in them, gold or platinum?
I haven't seen any, I've seen ones that have bits of diamonds in them, which I was wanting to buy one of those but couldn't afford it. But I haven't seen any that listed having those elements.
These might have some of that, but in such small quantities.
Parts per million.
I'm sorry, I didn't hear what you said.
You can't see the metal.
Well, somebody was talking back there, I didn't hear what you said.
If you assay it, it's there.
These probably have some very small quantities of that, but not chunks.
Right. Yes?
So as to the origin of these, is it assumed that they were planetesimals that broke up? And is there a clear understanding about these originated as like in the accretion, just like the planets, and then they broke up? What I'm a little bit puzzled about is how the asteroids coagulate from the gas that was originally.
Well, they first start, it's static in the formation of the solar system. The bits gather together, they have determined not from gravity to cause them to stick together, but static causes them to get together in the smallest clumps. And then when they're big enough to actually have enough gravity, then that kind of escalates the situation, and they start clumping together.
These things would never have enough gravity to contribute.
Well, they form with gravity. They start forming with when they start forming with static, that's just the little bits, the littlest bits, but then it's the gravity comes in, and that's how we get planetesimals by that's accretion, that's the formation of the solar system. Starting with static and then moving. I think actually if we go back to, there might be a little bit more detailed explanation in it at the very beginning.
So that one that's in that last batch that you sent
Hold
out.
on a second, let me just look at this here and proceed with this question. This might talk about it. Cosmic grains of dust collide and stick through static to form larger bodies. When they reach approximately 1 kilometer, then they can start attracting with gravity. So it's static up to the 1 kilometer point, and then gravity, and then gravity really takes over and escalates, and then they start forming into protoplanets.
Were larger than 1 kilometer at some point, and then broke up again, or?
Exactly.
Last question. Right here. What was that?
That one that you were sending around, that's black on the outside and has sort of a creamy marshmallow inside. How did that black crust form? when and where?
The fusion crust would have formed in the Earth's atmosphere.
Okay, so it wasn't like that before, it just
Correct.
came.
It's a meteoroid, it was not that way.
Exactly.
Okay, thank you, Sandy. Big round of applause for Sandy.
And I don't know if we're allowed, if, I know a lot of people did not get a chance to look at the meteorites. I'm willing to stay. Are we willing, is there room still available for people to?
Yeah, we have to be out, generally as soon as possible. We can probably stick around for another 10 minutes before the thing.
Don't forget gastronomy.
Okay, so for those, maybe we can speed up the process and not take quite so much time looking at the meteorites so everyone can have a chance to at least see them.
National Coney, and Amanda, you want to continue your astronomical discussion? Thank you for coming tonight.
Yes.
I'll bring my meteorites over to the Coney Islands, so if you didn't get a chance to actually see them here, we can spend some more time looking at them up close there.
Astronomy after astronomy.
So yeah, we have to have an order of about 10. So I don't know.
Well, that isn't, I think it will.
Yeah, I didn't even get my name tag.
That's it.
Oh.
I know, but
Yeah, I somehow fell down and Jonathan, mine is not in my bag, but I